Hi and welcome, my dear friends of the underwater world. Since someone asked me about gradient factors in my video on decompression theory, I'd like to bring this topic forward and explain to you today what lies behind these so-called GFs and why your body's theoretical limit is not a straight line. Here, to understand this topic, however, we first need to take a closer look at M values. The M value describes the maximum tolerable excess pressure of an inert gas, typically nitrogen and diving, in a human tissue without causing life-threatening DCS, the decompression sickness. If you'd like to learn more about this, feel free to watch my video on decompression theory mentioned in the beginning. I've linked it below in the video description. Yeah, so far the good. But now we need to consider that recreational and technical diving operate under different conditions. And that means that in recreational diving, the M value is considered static and dependent solely on the tissue or the compartment. In technical diving, it is recognized that M values behave dynamically and depend on both the tissue or the compartment and the depth of the dive. The deeper you dive, the higher the M value. In summary, the M values describe the theoretical limit for tolerable supersaturation. Above this limit, the risk of decompression sickness increases significantly. And don't forget, a distinction is made between the static M value in recreational diving and dynamic M values in technical. Here, and so the M value at the recreational diving is based on the surface. We call this value M0, and M values in technical diving depending on the tissue and the compartment and the current diving depth. But let's take a look at this graphically. On the x-axis, this is the right one, we have the ambient pressure, which means that the deeper we dive, the higher it rises, so we move further to the right. On the second axis, the y-axis, upward one, we have the inert gas pressure within our tissues. This means that the more saturated we are with an inert gas, such as nitrogen, the higher we are on the graph. Next, we draw a straight line from the bottom to the top on the graph and label it P0. This is the pressure at the water surface. In most cases, 1 bar at a depth of 0 meter. Now we'll draw a few more lines. In green, we have a line that we would follow if the ambient pressure were equal to the inert gas pressure in the tissue. Since the inert gas fraction in our breathing gas is always only a fraction and never 100%, there is also a second line in blue. This line, that's the inert gas pressure in the breathing gas equal to the inert gas pressure in the tissue and rises somewhat less steeply than the green line. If we were to descend and theoretically remain at exactly the same depth for an infinitely long time, our tissue inert gas pressure would continue to saturate and eventually equal the inert gas pressure in the breathing gas. Then we would be exactly on this line. In practice, however, we are always below it when we descending. But more on that in a moment. First, let's look at one last line, the M value line. This line is slightly steeper than the green line and shows how the M values increase with ambient pressure. That is, as depth increases. We already learned that the point where the M values intersect with the ambient pressure, this is called M0. And now, let's go diving together. I've already mentioned that when we descend, we are below the blue line. our tissues slowly become saturated, and only if we theoretically remain at a depth infinitely, we eventually reach the blue line. But at some point, sadly, we have to surface. That is, the ambient pressure drops and the tissues desaturate. Not immediately, but with a delay, meaning we approach the M value line. The goal is always to dive below the M values to avoid DCS as safely as possible, and when we reach the surface, we should not be above the M0 value. Okay, now we've covered all the basics. We are ready to understand gradient factors. Let's take a look at this graphically. Gradient factors simply indicate what percentage of the maximum allowable supersaturation, that is, the M value, is permitted. We can visualize this as the distance from the M value line. A gradient factor of 100% corresponds exactly to the M value, and while 0% corresponds to the ambient pressure, though it becomes clear the smaller the gradient factors, the more conservative your dive will be. However, gradient factors are always specified as a pair. We'll look at that next. Let's take the combination 40-80 as an example. The first number in this case, 40, is referred to as GF low and describes the maximum tolerable overpressure of the inert gas in the tissue during the first safety or decompression stop at the depth. The GF high, in this case 80, also describes the maximum tolerable overpressure of the inert gas in the tissue, but upon reaching the surface, and thus determines the possible supersaturation at the end of the ascent. Since a picture is worth 1,000 words, let's take another look at this graphically. We take our previous graph and plot the two gradient factors, 40 for the GF low at the depth and 80 for the GF high at the surface. This is for sure on the P0 line. During our ascent, we remain below this line, which is formed when we connect the 2 points, whenever possible. As our nullimate step, let's take a closer look at the two gradient factors and what they mean. Well, start with GF low, the gradient factor for depth, for example, the first safety stop. This is actually the more complex one of the two factors, as there is less data available for. And one might be tempted to argue that a lower GF low is also more conservative, but a lower GF low also results in deeper stops. The idea behind this is to minimize bubble growth early on. However, we must not overlook the fact that a longer stay at depth also leads to further tissue saturation in the other compartments and the other tissues, and the entire decompression process takes longer due to subsequent desaturation, while decompression time is limited by a supply of breathing gas. The current trend is to avoid setting the GF low too low. The GF high is much easier to understand. Since this represents the time of surfacing, we are no longer diving over that point, which means we no longer need to account for further desaturation or our breathing gas supply. Here it can be said that a higher supersaturation value, that is a higher gradient factor, also entails a higher risk of DCS. So there, on the first look, is no reason not to choose a lower value, but consider also here longer deco stops and plan your breathing gas consumption in the depth. However, I look to emphasize once again at this point that the factors contributing to a DCS are not yet fully known or understood, which is why you should always dive conservatively. Here. So, in principle, that's all you need to understand the concept of gradient factors. To wrap things up, however, I'd like to take a closer look at three basic combinations. We'll start with GF low is bigger than GF high, meaning we surface with a lower level of supersaturation. Then we had at our first decompression stop at the depth. The permissible supersaturation thus decreases continuously during the ascent. However, this isn't necessarily more conservative or safe. It's only safer at the very end of the dive. Furthermore, there's little practical experience with such combinations, and many dive computers prohibits this setting. Here, the situation is different when the relationship is reversed. The GF low is lower than the GF high. This is the most common combination of gradient factors chosen when starting with conservative decompression and then gradually increasing it. However, it also leads to additional tissue saturation during longer stays at the depth. Here, and a very specific case arises when we set GF low equal to GF high, meaning that the gradient factor and thus the tolerated supersaturation remains constant through the entire ascent. However, according to current findings, this combination does not provide any primary benefit in terms of overall safety. The conservatism depends solely on the selected factor, which is what we have already discussed. Low factors result in earlier stops and long total decompression times, which is considered very conservative. Conversely, high factors lead to short decompression times with a higher permissible tissue supersaturation, which is then less conservative. Yeah, and we're really done now. As always, I hope you enjoyed the video. Please give it a like and leave a comment. Feel free to let me know if you understand the topic better now or what other topics interest you. I put them on my list for the future videos. And if you don't want to miss any videos, please subscribe to the channel. It costs nothing, but it helps a lot. So, thanks for watching the video, and until next time, I'll say all time good air and ciao.